Hello, chemistry students. Today we are doing our first lesson for the week of April 13th. This is officially a new unit. The last 3 weeks have been the gas laws unit, and now we're getting into solutions unit. There's much less math and calculation in this unit, more vocabulary and concepts. So what our goal for today is to be able to classify matter as an element, compound, or mixture. Okay. Now there's matter, we said, as anything that has mass and takes up space, but we can further subcategorize two types of matter. Okay. So if it has mass and takes up space, basically if it's made of stuff on the periodic table, it can either be a pure substance or a mixture. Okay. And then each of those can get broken down into two further categories, which we have on this next flowchart. Okay. So in the notes that we provided through Canvas, these two boxes were empty. So again, matter is anything that has mass and takes up space. We can either classify it as a pure substance, which means it's not mixed with anything. And if it's a pure substance, it can either be a chemical compound, which would have a chemical formula, chemical bonds, or it can be just a single pure element, gold, holmium, neon, those types of things. For mixtures, we have two types of mixtures. That would be heterogeneous mixtures and homogeneous mixtures. So this is really all we're going to be talking about today. Your homework is going to be classifying different types of matter into basically these four subcategories. All right, we'll start with our two pure substances. So the first is element. An element can't be broken down any further by ordinary means. So that means there's no decomposition reaction or single replacement reaction that can break down an element. Only a nuclear reaction could. And we're not talking about nuclear chemistry right now. So they're found on the periodic table, and they're usually found as a single atom. So what that means is just Ne for neon, or just HO for holmium. Sometimes, if you notice up here in the top right-hand corner, this would still be considered a pure element because we talked about the 7 diatomic elements, so O2, an O2 molecule. It's still pure oxygen, okay? And I'll help you guys make sense of this in our next examples. So if it's a pure substance, it could be an element or a compound. Now, compound C, chemical C, okay? So chemical compounds can be broken down by chemical reactions, and they're made of 2 or more elements that are chemically bonded. Okay, so now we're talking about water, H2O. I've got 2 pure elements in a bond with each other. Chemical compounds have a formula that doesn't change. We spent a lot of time first semester learning how to write ionic and covalent formulas. Okay, so those are all examples of compounds. And then the compound has new properties that are not the same as the original elements. And I've got an example here on this next slide for you. So pure sodium is an alkali metal. It's got 1 valence electron. It's a very malleable, lustrous metal, which means soft and shiny. It blows up when you put it in water. It's just very volatile. Okay. Pure chlorine gas has this yellow tinge to it. Chlorine gas is incredibly dangerous. It will burn your eyes out by turning any moisture it comes in contact with into hydrochloric acid. It's odorless. It has this yellow color. Both of these will kill you if you touch them or breathe them in or consume them in any way. But when they chemically bond to form a compound, you get sodium chloride, which is just table salt, which you have to eat every day in order to live. Okay, so that's what we mean when we say they take on new properties, right? Deadly, deadly, essential for life. Okay, all right. Examples for this, elements on the left and pure compounds on the right. You will notice there's something in parentheses, right? And we're going to always give that to you just because it gets really hard otherwise. So carbon, I put the chemical symbol, C. Oxygen is O2. Still, I just have 1 capital letter here, so I know that that's a pure element. Gold, capital A, little u. I know that's an element. Neon, okay, there's hundreds more. So if it's just on the periodic table. Now, compounds are going to have 2 or more elements, which means 2 or more capital letters. That's how you would know that we're trying to get you to answer compound. So hydrogen and oxygen bonded together, compound. NaCl, 2 elements. Glucose, C6H12O6. There's 3 elements. I would still consider that a pure substance, and it would be a pure compound. Okay? So that's how you're going to be able to recognize these on examples on your homework today. Example problems. Okay? I think these exact problems might even be on your little homework check today. So it says, number 1, a substance that cannot be separated into simpler substances by physical or chemical means. So which one of the 4 can't be broken down any further? That would be element. It's already as simplified as it can be. Number 2, a chemical combination of 2 or more elements. And chemical, C, should be a dead giveaway that it's compound, C. Number 3 and 4, which of the following is an example of an element? Okay. Again, your best bet is going to be looking at the chemical symbols or formulas we give you. So example of an element can only have 1 capital letter. It's just the element symbol for copper. With 2 capital letters, this one would be a compound. With nothing in parentheses, this is going to be a mixture. And then D would be a chemical compound as well. Number 4, which of the following is an example of a compound? Okay, take a look, see what you think. That'd be water. Okay, I'm seeing a chemical formula with 2 or more pure elements. So hopefully with those little tricks, this shouldn't be too hard for y'all. Okay, mixtures then. Mixtures are a physical combination. So that'd be like mixing blue jelly beans and red jelly beans. Okay, they're not going to turn green or purple. They stay blue and red. They just get mixed up. Okay, and then you can separate a mixture with physical means. So either by just picking out the red jelly beans, or by evaporating water, or by filtering out the noodles when you're making mac and cheese. Okay, and then the components of the mixture keep or retain their original properties. So salt water is a mixture of 2 compounds. Okay, so I've got NaCl and H2O. I can evaporate the water out and have the salt left. That'd be a mixture. Chocolate syrup plus milk. You still have milk, you still have chocolate syrup. They're just a solution now, a mixture of it. Okay, other examples. Salt water, sugar water. Okay, you see that you have 2 chemical compounds there. Air is an example of a mixture. Okay, it's mostly nitrogen. And then brass. This is one that if you have a periodic table handy, brass is a very, very common metal, but it is not on the periodic table because brass isn't an element. It's what's called an alloy, which means it's a mixture of copper and zinc. So you'll notice I didn't put a chemical symbol after the word brass because it doesn't have one. So that's how you would know that that one's a mixture. Okay, our 2 types of mixtures are heterogeneous and homogeneous. Now, you've heard those prefixes before, hetero and homo, okay? In biology, you learned about genetics and heterozygous alleles and homozygous alleles, okay? So hetero is the prefix that in Greek means other or different, okay? Homo is a prefix that means the same or uniform. Okay, so a heterogeneous mixture is a different or other looking mixture. So I can see there's the blue half and there's the purple half. A homogeneous mixture is going to look the same. So I can see that I have different elements mixed in here, but there's not a blue half and a purple half. It's more uniform. Again, here's the official notes on that. 2 types of mixtures, homogeneous. Homo means the same. It's going to look, to your naked eye, it's going to look uniform or the same throughout. Now this is a big one. I put it in red. They're also known as solutions. So the name of this unit we're working on is the solutions unit. If we wanted to be extra, we could call it the homogeneous mixtures unit because they're the same thing. So a solution of anything is going to be a homogeneous mixture, whether that's a Kool-Aid solution or a hydrochloric acid solution or a, I have no idea, solution. Solution means homogeneous, okay? Heterogeneous, other, different looking, not uniform, okay? So I see trail mix. I can see the cashews and the raisins and the M&Ms. There's the difference, okay? So it's a different mixture, a hetero mixture. right? I'm going to take you through some examples before I turn you loose. So examples that we love to use in chemistry for homogeneous mixtures: air. There's not oxygen in one room of your house and nitrogen in the other room. That would be very dangerous. They're same or uniformly mixed out, okay? A salt water solution, a sugar water solution, brass, because that instrument looks the same to your eye, okay? Those are all homogeneous. Soil, and I have a picture there. You get a handful of sand, okay? You can see different types of minerals and such in there. Sand and water, they don't dissolve. You can see the different types of materials in this granite or in this salad. They look different, okay? Here we go. Salt water solution. I would consider that homogeneous. The salt has dissolved, you can't see it. As opposed to this one, I've got oil, water, and sand. Oil and water don't mix, and sand and water don't mix. So I can see the different or hetero areas, okay? So that would be a heterogeneous mixture. M&Ms. Looks different. I see different colors for sure. Also, if you take a little nibble out of it, you can see the candy shell and the chocolate in the middle. So hetero, different. Black coffee. That was going to be homogeneous. You can't see where the different acids and caffeine molecules and water molecules are. They're uniformly spread out. Kool-Aid solution, got to be homogeneous. You can see the differences, so that would be hetero. Solid brass, okay? So if you're looking at this brass instrument, the trumpet, you can't see the different copper and zinc atoms. Even if you zoom in, you can see the differences, but they're uniformly spread out, so that means same, homogeneous. What about pure gold? Careful, that's a trick question. Pure gold is not a mixture, it's an element, okay? That was a mean one, that's fine. But pure gold, AU, is on the periodic table. All right, so last thing then. You have this checklist. 2% milk from the store. Is it same homo looking or is it different hetero looking? And unless your milk is very old and it's gotten green and chunky, guys, yikes. It should be homogenized and homogeneous. Mint chocolate chip ice cream. That's my brother's favorite. It's like the green ice cream with a little chocolate chunks in it. You can see the differences, so that'd be hetero. Italian salad dressing before you shake it. It's got a lot of oil in it, so you have to shake it before you use it because you can see the different areas. Elmer's glue looks the same. There we go. A handful of soil or dirt is going to have like little bugs and rocks and all kinds of stuff in it. Sugar water solution has to be homogeneous. Air in your classroom better be homogeneous for the most part. Okay. That's what your homework's going to look like today. It's really pretty quick. Last little plug for this, okay? I think we're up to 4 or 5 extra credit labs on the homepage. They're very fast. They're actually really kind of fun. You get lots of extra credit for them. Some of them you can eat afterwards and they're yummy. So take a look at your teacher's Canvas page and start sending in those extra credit labs. Thanks, y'all. Appreciate ya.